Hello students, good morning. So far we have completed the first unit, that is dilute solutions and colligative properties. Please students, watch all the videos and complete your notes, okay? And also start preparing for your exam. Fine students. So today I am so happy that we are going to start the second unit, that is phase rule. Okay, so this phase rule you haven't come across in your intermediate level. So each and every topic will be new for you students. Okay, so are you ready? Shall we start? So put the heading phase rule. Phase rule. So take a fresh new page and put the heading phase rule students. So let us do some introduction. So generally each and every chapter, if we know some introduction, then it will be easy to learn the topics. So now what is the introduction for this chapter, that is phase rule? For this, we should know what a system is. Next, what surroundings mean and what a boundary is. Okay? So students, we should know what a system is, what surroundings mean and what a boundary is. Okay? Now, coming to system, anything, okay, any material in universe which is under study or observation, we call it as system. What is system students? Any material or anything in universe which is under observation or which is under study, we call it as system. Okay? Then what is surroundings? Rest of the system we call as surroundings. Then what is a boundary? The real or imaginary line which separates system from surroundings is called as boundary. Okay students? The real or imaginary line which separates system from surroundings is called as boundary. Okay? Now let us concentrate on system. Okay, let us concentrate on system. Suppose students, if the system has only one phase, okay, we call it as homogeneous system. What is it students? If the system has only one phase, we call it as homogeneous system. For example, if it has more than one phase, means two phases or more than two phases, then see I am writing here, if the system has two or more phases, then we call it as heterogeneous system. Heterogeneous system. Okay? So, did you get the clarity students? If it has only one phase, then we call it as homogeneous system. If it has more than one, that means two or more phases, we call it as heterogeneous system. Okay students, now let us concentrate on heterogeneous systems. Okay, so in this phase rule, we are going to learn about heterogeneous systems. So to understand the behavior of the heterogeneous systems, a scientist or an American physicist by name Willard Gibbs. Willard Gibbs. He was an American scientist. He proposed a rule in 1874. Again to repeat, students, in order to study or know or understand the behavior of heterogeneous systems, an American scientist by name Willard Gibbs, he proposed a rule in the year 1874 which is called as Gibbs phase rule, or simply phase rule, which goes like this, students. It is given mathematically as F is equal to C minus P plus 2. Put it in a box, students. This is called as Gibbs phase rule expression. Okay, students, I started with the system. What a system is. If it consists of one phase, what is it is called as? If it is consists of more than one phase, what it is called as? So heterogeneous system is the system which has more than one phase, that is two or more phases. It is called as heterogeneous system. So in this chapter phase rule, we study about the behavior or we know about the heterogeneous systems. So in order to understand about a heterogeneous system, there was a scientist by name Willard Gibbs who proposed a rule which is given mathematically as F is equal to C minus P plus 2, which can be called as phase rule expression. Okay. Now, immediately we should know what F is, what C is, what P is. Right up. Where P is number of phases, where C is number of components, and where F is number of degrees of freedom. Okay, students? So, are you learning, ma? We are going step by step. Okay? So, where F, number of degrees of freedom, C, number of components, P, number of phases. Next, what should we know? We should know what a phase is, what a component is, and what degrees of freedom are. Ready? Okay. Now, put the side heading. Put the side heading, students. Phase. Put the side heading phase. So what is a phase? Okay. Now you know what homogeneous system is, what heterogeneous system is. In phase rule, I told you we are going to study about the heterogeneous systems. Okay. Now let us consider a heterogeneous system which has two phases. This is one phase, for example A. This is one phase B. Okay. So, if we look at only A, it is homogeneous by itself. Okay. If we look at B, it is homogeneous by itself. Okay. But both are different. A and B. Okay. So, it has two phases, students. What are they? A and B. Fine. A and B. So, A is homogeneous by itself, B is homogeneous by itself. Okay. So, total this is a heterogeneous system. Okay. So, which has two, or students, it might have one more part. If I write, it is a C. Okay. So, any heterogeneous system having two or more homogeneous parts. Okay. What are they? Two or more homogeneous parts, which are, students, looking at this, we can distinguish between the two phases. You can say this phase is A, this phase is B. Okay. So, we call it as physically distinct. Physically distinct. You might know the meaning of physically distinct. That means they are distinguishable physically. Okay. And mechanically separable. What is the meaning? Mechanically separable means we can separate them easily. Okay. So, Any heterogeneous system has two or more homogeneous parts which are physically distinct and mechanically separable, and these are called as phases. Okay students, hope I made it clear, right? So you can write down the definition. Any heterogeneous system has two or more homogeneous parts which are physically distinct and mechanically separable, and these are called as phases. Written. Shall we know the examples now? Put the side heading examples. So write down the example students. A. Suppose if we take gases students. Okay. Suppose you take gases. So as we all know, all these gases are miscible. That means they get mixed up with one another. Therefore, we can say that all gases constitute one phase. Okay, you can write down all gases constitute one phase. Okay, next coming to liquids. Students, in liquids there can be two types. What are they? One is miscible and the other one is immiscible. What is the difference between miscible and immiscible students? Miscible means they get mixed up and they look, we can see it as one phase, and immiscible means they are not mixed up with, that means they cannot be mixed up with one another. Okay. So, if the liquids or if we consider miscible liquids, they constitute only one phase. Okay. For example, water plus ethyl alcohol or benzene plus chloroform. Okay. So, miscible liquids constitute one phase, whereas immiscible liquids, depending upon the number of liquids present in the system, we can count the phases. For example, if there are carbon tetrachloride and water, then we can say there are two phases. Okay. So, immiscible liquids constitute different phases. Miscible liquids constitute only one phase. Okay. So, this is about the phases in liquids. Next, coming to another example. Write down C. Decomposition of CaCO3. Decomposition of CaCO3. Can you write the reaction students? Decomposition of CaCO3. Look here, I am writing calcium carbonate decomposes into CaO plus CO2. Okay. So, calcium carbonate solid phase, calcium oxide solid phase, and carbon dioxide gaseous phase. So, there are two solid phases and one gaseous phase. Hence, we say that this heterogeneous system has three phases. So, P is equal to 3. Understood students the concept phases? Okay. So, what is a phase ma? Any heterogeneous system consisting of two or more than two homogeneous parts which are physically distinct and mechanically separable. These are called as phases. You can write down all these three examples. Okay. Next, moving on to the second one. Put the side heading number of components. Write down the put the side heading students. Number of components. So, what are these components students? So, I will not come from the definition. First, we will look into an example, then we will define so that it will be easy for you. Okay, students? So, what is the example that we can take here? For example, take water system. Okay, water. Water can exist in how many phases, students? Three phases. What are they? Solid, liquid and vapor. Okay. So this is solid phase, ice, liquid phase, water and vapor phase, water, vapor. Okay. So this is solid, liquid and gaseous phase. Fine. Now suppose if I ask you the formula of water, you will tell me H2O. If I ask you the formula of ice, H2O. If I ask you the formula of water vapor, H2O. Okay. So in order to explain the composition, the chemical composition of ice or liquid water or water vapor, we need or we require only one component, that is H2O. Okay. So in order to explain the chemical composition of any phase, that is solid or liquid or vapor of water system, we require only one component, that is H2O. Hence, water system we can call it as a one component system. Write down, students. C is equal to 1. That means water system is a one component system. Okay. This is example number 1. Next example, take sulfur system. Sulfur system. Sulfur system can exist in 4 phases. What are they? Rhombic, monoclinic, liquid and vapor. So what are the 4 phases, students? Solid phase, liquid phase and gaseous phase. Okay. So if I ask you what is the chemical that we require to explain rhombic phase of sulfur system, you can tell me sulfur. Next, monoclinic, sulfur, liquid sulfur, sulfur and vapor, sulfur in vapor phase, it is also sulfur. So how many components or how many chemicals do we require to explain the composition of each phase present in sulfur system, students? Only one, that is sulfur. Even though there are 4 phases, we require only one chemical, that is sulfur, to explain the chemical composition of any phase in sulfur system. So again it is a one component system. Okay, understood now? Next, third example, students. Third example, put the side heading, decomposition of calcium carbonate. So write down the reaction. Decomposition of calcium carbonate. You know there are 3 phases. What are they? Solid phase of calcium carbonate, solid phase of calcium oxide and gaseous phase of carbon dioxide. Okay. So how many phases, students? 3 phases. P is equal to 3. Now, how many component system is decomposition of calcium carbonate? Okay. So in order to explain the chemical composition of each phase in this particular system, we need any 2 of these 3 chemicals. How, ma'am? I will tell you. Okay. How many components are required, students? Any 2 of 3 chemicals can be used to explain the chemical composition of all the 3 phases in this particular heterogeneous system. Ready? Okay. Number 1. Taking CaCO3 and calcium oxide. Students, carefully concentrate because most frequently this is asked. So how do you determine number of components in the system decomposition of calcium carbonate? Okay. So one example, if you understand, remaining you can write on your own. Don't worry, I will be giving those set of examples also. Okay. Now, So taking these two chemicals, what are they? Calcium carbonate and calcium oxide. How many phases are there? 3 phases. Okay. So let us explain CaCO3 phase. Okay. Let us explain CaCO3 phase taking CaCO3 and CaO. Look here students. CaCO3 phase can be explained like this. CaCO3 plus 0 into CaO is equal to what? CaCO3. 0 into anything is 0, as you all know. Okay. So CaCO3 phase can be explained taking these two chemicals in this way. Okay. Next below. CaO phase. Calcium oxide phase. How will you explain taking CaCO3 and CaO? So similarly, like this, 0 into CaCO3 plus CaO is equal to calcium oxide. Got it? Next. Now comes the difficulty phase, CO2 phase. CO2 is not there in these two. Then, how will you write? So, CaCO3 and CaO, we can utilize these two chemicals to get the carbon dioxide. How students? CaCO3 minus CaO is equal to what? Carbon dioxide, CO2. Okay. So we explain CaCO3 phase. We explain CaO phase. We explain carbon dioxide phase. How? By taking only two chemicals out of 3. Okay. Next set. Second set. Second set, CaCO3 and CO2. Okay, write down. Second set of chemicals, CaCO3 and CO2. Okay, ready students? Now, first, CaCO3 phase. So, how will you explain calcium carbonate phase taking CaCO3 and CO2? How? Understood now? Some of you must have already written in the book. Okay, very good. CaCO3 plus 0 into CO2. 0 into CO2 is equal to what students? CaCO3. Next, CaO phase. CaO phase is not at all there. That means CaO is not at all there in these two. So, how will you write? CaO phase. Shall I write here? Yes, CaCO3 minus CO2 gives you calcium oxide phase. If you subtract CO2 from calcium carbonate, you will get CaO. Got it? Next, CO2 phase, how will you get students? CO2 like this, 0 into CaCO3 plus CO2 gives you CO2. Therefore, we could explain calcium carbonate, calcium oxide and CO2 taking these two chemicals. One more set of chemicals also we can take to explain the composition of all the 3 phases. What are they students? What are the remaining ones? Yes, CaO and CO2. Write down. Third set of chemicals, CaO and CO2. Fine. Now, let us explain CaCO3 phase. So, how do you get CaCO3 from CaO plus CO2? It is in front of you. So, here directly you can write down CaO plus CO2 gives calcium carbonate. Got it? Next, CaO phase, how will you get students? CaO phase, right, CaO plus 0 into CO2. Okay, next CO2 phase. CO2 phase, 0 into CaO plus CO2 gives you carbon dioxide. So now tell me the number of components of decomposition of calcium carbonate. How many? 2 components. So, phases equal to 3, components equal to 2. Therefore, we call it as a two-component system. Where water is a one-component system, sulfur is one-component system, decomposition of calcium carbonate, two-component system. Okay. So, we require two chemicals to explain the chemical composition of each phase in a heterogeneous system. These are only the example, students. We have not yet defined. Now write down the definition. Write down the definition. The minimum number of, write up, the minimum number of independently variable chemicals required to explain the chemical composition of each phase in a heterogeneous system, either directly or in the form of a chemical equation, are called as number of components. Full stop. Are called as number of components. Understood, students? So next one, degrees of freedom. We have completed number of phases, number of components, and the next one is number of degrees of freedom. So before going into degrees of freedom, I will tell you two sentences, students. Okay, you should remember these 2 points. So, in order to define the state of any system, we require factors like pressure, temperature, composition or concentration and volume. Generally, these are the factors used to define or required to define the state of any system. So, out of these 4, most frequently pressure, temperature and composition are used. Okay. And among these 3 also, for one component system, we use these 2 factors, pressure and temperature. Okay. So, for 2 component systems, we will take composition or concentration into consideration. Understood? Clear, students? Now, I will tell you what degrees of freedom are. For this also, we will go from examples to definition. Okay. So, then it will be clearly understood. Okay. So, for example, students taking water system. I told you water system can exist in 3 phases. What are they? Solid, liquid and vapor. Okay. Solid, liquid and gaseous states. For example, if we assume that water system exists only in solid phase or liquid phase or gaseous phase. Okay, only one phase. Let us assume that water system exists in only one phase, either solid or liquid or vapor. Okay. So, only one phase. Phases we denote with the P, right? So, P is equal to 1. You all know, just now we have learned water system is a one component system. Why? Because we require only one chemical to explain the chemical composition of all the 3 phases, right? Now, my question. What is the phase rule expression? Phase rule expression, F is equal to C minus P plus 2, proposed by whom? Not me. It was proposed by Willard Gibbs. It is called as phase rule expression. So you have C, you have P. Okay. So from those values or from these values, we can determine F. Right? Shall I substitute? Is equal to C1, P1 plus 2. 1 minus 1 plus 2 is how much? 1 minus 1 plus 2 is 2. So F is equal to 2. So what is F? Degrees of freedom. So when water system is assumed to exist in only one phase, then F is equal to 2. That means it has 2 degrees of freedom. Okay. Then the system is said to be bivariant. Okay. So for F is equal to 2, system is called as a bivariant. That means it has 2 degrees of freedom. What is the meaning? 2 degrees of freedom. I told you most frequently for a one component system we require 2 factors, pressure and temperature, to define the state of a system. Okay. Now coming to 2 degrees of freedom. So when F is equal to 2, that means that you can change temperature and you can change pressure, and water system exists as only one phase. No change in that phase. Even if you change temperature, even if you change pressure, both the values of these 2 factors can be changed. This phase exists like that phase only. Okay? Understood now? That's the meaning. F is equal to 2. That means the bivariant system which has 2 degrees of freedom. Okay? If you don't understand this one, no worries. Next example, you will understand. Okay? One phase is done. Now let us assume water system existing in 2 phases. It's your wish. Solid liquid or solid gas or liquid gas. Any 2 phases, let us assume that water system is existing. Now P is equal to how many? How many phases? 2 phases. Components we know, one component system. Now let us calculate degrees of freedom from the expression F is equal to C minus P plus 2. Substitute. C is equal to 1. P is equal to 2. 1 minus 2 plus 2 is equal to 1. That means degrees of freedom only 1. Then the system is called as univariant or monovariant. Okay. So when F is equal to 2, it is called as bivariant system. When F is equal to 1, it is called as univariant or bivariant. Now, what is the meaning? F is equal to 1. When F is equal to 2, we can change both the factors without change in the phase. Okay? F is equal to 1 means you can change either temperature or pressure without changing the phases present at equilibrium. Okay? Keeping pressure constant, change the temperature. Those 2 phases will be like that only. Okay? Keeping temperature constant, change pressure. Those 2 phases remain like that only at the equilibrium. Understood? If you don't understand this one, then we will go to the final example. It will be clear and it will be crystal clear. Okay? Now, third set of examples. So, one phase is over, 2 phases are over. Next, third phase is, let us assume that water system exists in all the 3 phases. All the 3 phases. That is solid, liquid and gaseous phases. Now all the 3 phases are at the equilibrium, students. Okay. So phases how many? 3. Components how many? 1. So F is equal to C minus P plus 2. So C minus P plus 2. Substitute. C 1, P 3 plus 2. How much? I want your answer in the comment section. I want your answer in the comment section. How much? Yes, it is 0. F is equal to 0. Okay. So, for F is equal to 0, the system is called as invariant or non-variant. Non-variant. Now tell me, what is the meaning of non-variant or invariant? When F is equal to 2, what did I tell you? Both the factors you can change without changing the phase. When F is equal to 1, you can change either temperature or pressure. That means value of one factor can be changed without changing the number of phases present at equilibrium. Then what is 0? You cannot change either temperature or pressure. If you try to change any of these factors, that equilibrium will be disturbed. Okay. So it has only one temperature and one pressure value. Those values I will be telling in the next class, that is water system. Okay. So here write down, for F is equal to 0, the system is invariant or non-variant. Changing the values of any of the two factors changes or disturbs the number of phases present at equilibrium. Once again students, F is equal to 2, bivariant. F is equal to 1, univariant. Next, F is equal to 0, non-variant. Okay. So, bivariant, both the factors you change. I need not worry. F is equal to 1, you can change one factor, either temperature or pressure. I will not worry. F is equal to 0, you cannot change either temperature or pressure because I will be disturbed. That means the equilibrium will be disturbed. Okay. Understood students? Hope I made completely 100% to 100% clear. Shall we define now degrees of freedom? Okay. So write down the definition. The minimum number of variables, which can be changed or varied, V-A-R-I-E-D, independently, which can be changed independently without changing the number of phases, present at equilibrium are called as degrees of freedom. So students, this is all for today, a new chapter. Okay. So I wanted to do only a little in the first class. Why? Because you shouldn't get or you shouldn't feel bored of this chapter. Okay. So till now I think or I guess you might have enjoyed the lesson. Okay. So what is the chapter that we have started students? Phase rule. Under that we have seen introduction, phase rule expression, what a phase is, examples, what are components, examples, what are degrees of freedom, examples. Okay. Kindly write down the notes for all these points, and next week we will be learning about water system under one component system. Okay. So see you next week. Bye bye students.